Today we're going to be deriving the Rachford-Rice equation. Rachford-Rice. Now, I'm going to define a system here. So we have some tank, and we'll separate it into vapor and liquid phases. So we have a two-phase system, and we will define this as a vapor-liquid system that's in equilibrium, which means that we need to have a defined pressure and a defined temperature to determine. Ultimately, the goal of a Rachford-Rice equation is to do a flash calculation to help us determine the liquid phase and mole phase, the liquid phase and vapor phase mole fractions in a system somewhat like this in vapor-liquid equilibrium. A couple other variables I'm going to define. I'm going to define a feed here, and we'll say that's 1 mole. And I'm going to define the composition of our feed. So something like, let's say, a 40-60. All right. So the first step is I'm going to create a very intuitive overall mass balance. So that'll look something like our overall feed is going to be equal to our mass in the liquid fraction plus our mass in the vapor fraction, the vapor phase, liquid phase and vapor phase. And that makes sense. Whatever we're putting in has to eventually separate out, but we have to conserve mass in this system. So something like this makes sense as an overall mass balance. We can then take that one step further, and we can create a component-based mass balance. So that'll look something like this. So our composition of component I times the overall feed. So this essentially gets us our mass that's in our initial feed, is equal to our liquid phase mole fraction in the liquid phase of component I plus our vapor phase mole fraction in the vapor phase of component I. And we're making the assumption here that we have some sort of binary system that's in a 40-60 mixture. So this could be any two chemicals that you could want it to be. For this one, we're going to choose benzene and toluene, and once you do that Python calculation, we'll get some pretty decent numbers for these derivations to make a little bit of sense. Okay, so now the next step, I'm going to introduce a vapor-liquid equilibrium relationship, which is essentially a ratio of our vapor phase and liquid phase mole fractions. And this is very useful to us because now we can get this side of the equation in terms of either x or y. I'm going to choose to keep it in terms of x. So we can rearrange this to solve for y, which is equal to ki xi. So now we have something that looks a little like this. So now we have this side of the equation remains untouched. This term also remains untouched, and now we replace our definition for y. So now we have the vapor-liquid equilibrium relationship times our liquid phase mole fraction times v. Now the next step I'm going to take here is I'm going to try and isolate this z here. And the way I write this is going to make a little bit more sense after this next step that I'm going to do. So I'm going to have this as xi L over f plus ki xi v over f. And now essentially what I've done is I can define a new term. So now I'm going to kind of use this relationship here. And I'm going to introduce a new variable phi, which I'm going to label as the vapor fraction. Vapor fraction. And the way I'm going to define this is I'm going to define this as the mass in the vapor phase over the overall feed. And we see that this term here now aligns with this term here. Now, what about what's going on over here in our liquid over feed? Well, that simply now just looks like 1 minus phi, and that makes a lot of sense intuitively. You have a vapor fraction, 1 minus your vapor fraction has to be your liquid fraction. Liquid fraction. So this looks like 1 minus v over f, but now if we look at it, well, 1 is simply just feed over feed minus v over feed. And if we rearrange this to f minus v, subtracting this to the other side, all we're left with is L. So this just equals L over f, which is this term here. So now we can use our variable phi, not sure how you guys say it, but I say phi. Now we have this in terms of our liquid fraction, and our vapor fraction is now in terms of this phi term, which makes this just a little easier to manipulate. All right. Now my next step is going to be trying to get this x isolated. And so to do that, I'm going to have to subtract over, let's see, how do I want to tackle this? First, I'm going to factor out xi because it's a like term on both sides. So xi, and then we have 1 minus phi plus ki phi, right? Then I'm going to want to divide this side over to this side. So I'm going to rewrite this like xi is equal to zi over, and I'm pretty sure 1 minus phi plus, let's just write this out over here on the side. So 1 minus phi plus ki phi. If I take this phi term out, I get 1 minus phi, and then 1 minus 1 plus ki, right? Actually, you know what? I don't want to mess that up too much. I think this is a good enough way to put this. So I'm just going to 1 minus phi plus ki phi. Now, something that we know is that if we sum up all the liquid phase mole fractions of all components I, so from, n equals 1 to I, something like that, simply this side just becomes 1. The sum of all of these mole fractions should equal 1. So now what we're left with is 1 is equal to the sum of zi 1 minus phi plus ki phi. And this, ladies and gentlemen, this equation right here is our Rachford-Rice equation. So now we have a brand new Python notebook here. As you can see, I've already imported a few things that will help us solve this problem. First, a list of libraries that'll be helpful to us, as well as importing this props library that will give us the properties for our system. So we remember we have a binary system, binary mixture of benzene and toluene. It's in a 40 to 60 ratio. And we also have some functions that I had written out in an earlier video that we can use to give us our bubble temperature, dew temperature average. So our problem statement, I guess let's start with that. Our problem statement states that we are running this flash calculation under atmospheric pressure, and our temperature will be an average of our bubble temperature and dew temperature at this given pressure. So running that calculation really quick. So bubble T at our composition and our pressure that we have stated up here. And we just want to return our temperature, which is just this output here. So we put this bracket 0 to signify that we only want to take out that first value that it's giving us. And it'll be something very similar for the dew temperature. So I'm just going to copy paste that over, switch this to dew temperature. Divide this whole thing by 2. And let's see what T is. Make sure all of this is ran properly. Oh, I see. Let's let that do its thing. Make sure that's a plus. And now that looks a lot better. Now the next thing that I want to also implement into this is, well, remember that we had that vapor liquid relationship, K. This one right here. Well, something that we can also say about K, well, we know that K is equal to our vapor phase mole fraction over our liquid phase mole fraction. And if we remember from Raoult's law, Yi is equal to Pi sat at some temperature T times our liquid phase mole fraction. Oh boy. I'm going to have to rewrite that. Times our liquid phase mole fraction all over the total pressure. So if we plug this Yi back into here, what we essentially end up getting is we cross out this Xi and we just get the saturation pressure over the total pressure. So we can also code that into Python because we can actually get that vapor phase, we can actually get that saturation vapor pressure. So I'll define another variable K, which is going to be equal to our vapor pressure at temperature T over the total pressure. And if we look at that, we have an array. So this is going to be the saturation vapor pressure for benzene. This is going to be the saturation vapor pressure for toluene at this temperature here. All right. Now we're ready to define our function. So first, I'm going to define a target function, and I'm going to call that RR0, the 0 of our Rachford-Rice. The input is going to be phi, because that's the one thing that we don't know about this equation yet. And essentially, by setting this up as a target function, we're shifting this 1 over to the other side. So we have a 0 equals sum of z, da 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 da, so that when we plug it into our root scalar solver, it knows that, okay, we're setting this function equal to 0, and then here is the value of phi that gets you there. So let's do that. So basically what we're going to be returning is that function that we had just stated. So z, it's going to be the sum, and p dot sum z over, was it 1 minus phi plus k times phi, I believe. Yeah, that looks right. And then all that, we'll subtract 1 from it. I guess that looks decent. So let's just run this really quick. So scipy dot optimize dot root scalar, and we're gonna have to give it a few things first. First, we're gonna give it the function that we want to zero out, the target function that we had just created. We need to give it an initial guess. So our initial guess is going to be for our phi value. So initially, let's just say that we have a 50-50 phase ratio between our liquid phase and our vapor phase fractions. So 0.5. Set this method equal to Newton's, or Newton's method, and let's just see what it does. Right. So optimize is telling us that our value did converge. We did get a root for this function here, which would be for our phi. So I'm just going to save that, repack that into phi, root. So now when we do that, it just gives us the value of phi that makes this equation true. I might have found a small little syntax error that might be messing up our values a little bit. Just having brackets around these, you know. You can never have too many parentheses, as I always say. Yeah. Now we find this value makes a bit more sense. It's a bit closer to our initial guess, and it's not an insanely low number. So yeah, now we have a good phi value that we can work with. And essentially now that we have this phi value, we can find our vapor phase and our liquid phase mole fractions for each component. And you might be wondering, well, how are we supposed to find that? Well, if we remember, we already defined what x is. X is the sum of this side here. Well, we already know what that is. It's just this much here. So x is equal to this. So now let's take a look at what x is. NP sum. Oh, no. We don't need the sum here. Now, it was just taking both of those values and putting them together, but we want to see what the individual compositions are. So this is actually going to be the liquid phase mole fraction of benzene. This is going to be the liquid phase mole fraction of toluene, because that's how we have it ordered here. And now y, well, instead of, you know, maybe going back to our whiteboard, going all the way back up here, and instead of doing everything for doing these steps again, but instead using xi is equal to yi over ki, simply what we can do is just use this relationship here. Yi is equal to ki times xi. So that's exactly what we're going to do. So now y is equal to k times x. And now if you look at these side by side, there we go. So now we have exactly what we need from our flash calculations. So easy enough, we're going to define a new function here. So we're going to define this as our Rachford-Rice. So we need 3 inputs for this function to work. We need, of course, we need our z, our compositions. We need our pressure, and we need our temperature. And actually what I'm going to do is I'm going to make this k calculation a part of my function here. Make sure all this is indented in. And simply, oh no, I just lost all that. That's all right, no matter, we can type that back out again. So x is going to be equal to, well, let me have this after here. So now x is going to be equal to whatever is in our parentheses here. All right. Oh no, I need my solve IVP. Aha. Or not my solve IVP, I need my my optimize. So SP to optimize. This is just gonna be doing it all over again. Oh, Gemini saved me here a little bit. So this is gonna be our phi is equal to that. And now we have x is equal to our, yes, that exactly. We don't want to return the x though. Make sure that this lines up with that. It seems to. Y is equal to k times x. All right, and we want this function to return our x and y. So let's see if this works. Rachford-Rice. I'll give it our inputs. And there you go, exactly how we drew it up before. Gives us our x and y as a function of our compositions, our pressure, and our temperature.